Okay. Lots of people. It's fun. Thanks all for coming to this talk today about reactive applications, how to build reactive applications. Titled Go Reactive, Event-Driven, Scalable, Resilient, Responsive Systems. It's a mouthful, but I'll try to explain why it's such a long title and everything that it really encompasses. So my name is Jonas Bonér. I'm the CTO of Typesafe. Typesafe is the company behind the Scala programming language, the Akka runtime, middleware, and the Play framework, and a whole bunch of other tools around that, around the platform. And we built systems to help you guys write reactive applications. So this talk will be a lot about sort of the underlying principles, why I think this matters, why I think reactive applications are important, and what kind of problems they solve, and also some of the wrong way of doing things, and why. So, as developers, when we have, I guess, all sort of experience that sort of the demands and expectations and the requirements and the environments that we have to write applications in and deploy in have dramatically changed the last 5 to 10 years. Today we need to write applications that manages and run on mobile devices, in multi-core architectures. I mean, it's really hard to find a single core hardware nowadays. Even the phones are quad-core machines. And that has a lot of implications. We need to deploy them into cloud computing architectures, scale out to massive users. Most things are exposed now, our applications are exposed now to the internet, which means that instead of having like thousands of users, now it's like tens of thousands or hundreds of thousands of users on a lot of applications. And on top of that, the sort of demands of the users have become much, much harder. I mean, the users doesn't really need to get sort of real-time feel in the applications. Applications need to be interactive. They need to be highly collaborative, not just with the server and the data you sync. It also needs to be collaborative across users, right, in the social kind of things and stuff like that. And they all need to be able to have sub-second response time on top of everything. So it's a really, really hard world we're thrown into it, as developers today. So I think we really need to rethink the way we do software, and that is already happening. And we need new tools for this new type of applications that needs to be built. So in short, I think we need to build systems that first react to events. Systems need to be event-driven nowadays. They need to be able to react to load. It needs to be fully scalable to make use of all the multi-core hardware we get, scale up, also as well as scale out on multiple machines if you deploy it on EC2 or Google Compute Engine or Heroku or whatever you do. They need also be resilient. I mean, systems just cannot stop today. They need to be fully available. Basically, 5 nines is almost a requirement today. And that's really, really hard. And I think that has a lot of implications on how we design software. We can't just deal with it later whenever there's a need. I mean, after deployment, etc. It needs to be something that we built into the application and think through from day one. We also need to react to users. Applications need to be constantly responsive, both during greenfield scenarios as well as under failure, under high load, etc. Okay? So in short, we need systems that react to a lot of things. And one name sort of for these type of applications that have come up, I mean, I didn't invent it. It sort of grew organically in very different communities, not just the Java or Scala community, I mean, on the JVM, where I'm coming from, but also in the JavaScript community and the .NET community, etc. All these communities have realized this problem and have tried to solve it in different ways, and start talking about these things as reactive applications. Okay, so what is reactive then? That's sort of what I will try to talk about in this talk. If you go to Merriam-Webster, the word reactive, when you think about it, especially if you're an English speaker, the word reactive English native speaker, the word reactive has a lot of sort of negative connotations. I mean, you should be proactive, not reactive, etc., etc. Right? But still, I think the word fits really well, because if you go to the original definition, it means readily responsive to an outside stimulus. And it's really the essence of what event-driven programming is all about. It's actually about being lazy, not use the hardware more than you have, not sit and pull, instead of push things when data is available, etc. So react to events, react to load, react to failure, and react to users. Okay. So the fourth core traits, if we sort of try to distill what it's really all about. Reactive is about a lot of things, like scaling, I mean scalability and non-blocking and all kinds of like buzzword, right? But if you really look at it at the essence, what are the core principles? And I think these are the four core principles. It needs to have an event-driven core. The event-driven core will enable you to scale things out, as we'll talk about. It will also be the enabler for fully resilient systems. I don't believe you can build fully resilient systems without having a fully event-driven core, and I'll get to why. And throughout all that, the system needs to be always responsive, full responsive. During load, during failure, or when things are going good. Okay. So the remainder of this talk, or the essence of this talk, is to talk about how can we get here? How can we build event-driven systems that are scalable, resilient, and responsive? Okay. So I'll talk a lot about principles here. I show you some code as well, and the code I'm showing is from the type of applications that I built. Right. It's going to be a lot of like code in Scala and Java. And also examples from Akka and Play, naturally, because that is the way, I mean, the world that I live and my colleagues live in. But all of these principles have really not much to do with that type of platform. It's completely generic. It works as well as on the .NET platform or running on V8 or wherever. These are core, fundamental principles that I think we all need to start thinking about and embrace. Okay. So, starting with event-driven. I tried to find an event-driven definition in Merriam-Webster. I could not, so I had to go to Wikipedia. So, event-driven is defined as the flow of the flow of a program when the flow of the program is determined by the events that is passed to it. Okay, that is event-driven. And first, taking a step back, why do we need event-driven systems? If you look at how systems have been built, I mean, the last 20 years, it's have sort of relied on shared mutable state, your classic von Neumann architecture, where you have ordering, linear ordering, you have the instructions, and changing the mutable state. The von Neumann architecture really brought us where we are today, but it's fundamentally not made for when things happen concurrently. Then you need to introduce things like locks. Okay, so I believe that in this new world, shared mutable state together with threads really leads to code that is totally indeterministic, or non-deterministic, I'd say. Indeterminism is something different. And really the root of all evil. I mean, Don Knuth he really had no clue what he was talking about. He hasn't experienced the pain of writing really concurrent system using shared mutable state, because it's really something that you have to avoid at all cost. Okay? One way out of that is to use immutable state. I mean, there's been a lot of trends about functional programming lately, but it's really nothing to do with functional programming more than it's one of the fundamental premises, but it works as well in OO, I think. It's something that we, functional programmers or OO object-oriented programmers, regardless, need to think about, managing immutable state. This, because if state is immutable, you don't have to take locks. You can share your state freely between threads, as well as other processes, etc., which is very nice. Okay, one of the core sort of essence of or characteristics of a fully event-driven system is that it doesn't block. Okay, you should never ever block. If you sit on a resource and block, that means that you're impeding progress. Someone else could probably make better use of that resource at that point in time, rather than just having you sit and wait for something to happen. Okay? So always use non-blocking. really kills scalability. It's actually the contention that kills scalability. If you have two sort of threads or two actors, two processes contending for the same resource. So always use non-blocking I/O. I mean, all the APIs that we use, most of them actually already have non-blocking versions, and use timeouts as well, if you have to use blocking, I'd say. But it's better to avoid it. Use lock-free concurrency, and that's hard, right? But the good thing is that there's starting to come up lots of libraries that do this for you very well. Akka is one of them. There are many others as well. Reactor was just released, for example. Vertex, been talking about Vertex here. There's really starting to brew in this ecosystem. We're coming up with a lot of good ideas how to solve these things well. Okay. And the other, non-blocking is one. The second one is async. You need to make sure that your program is fully async. And if you have these, then you have sort of the essence of an event-driven system. You should think in terms of workflow. I mean, how if you design your system using events, then sort of instead of having to deal with low-level plumbing about which lock you take to guard certain resource, etc., instead you start thinking about how the events flow in the system. You need to think in workflow, and workflow has semantics. It usually has high business value and high business semantics as well. So the nice thing, if you design your system like that, then you get all the nice things with event-driven as a natural sort of side effect, you can say. I mean, or this implies that it will run nice on multi-core architectures. That will also be well prepared to scale out on cloud computing architectures, etc. And it really gives you both lower latency and better throughput. And I think the most important thing is probably that it gives you extremely loosely coupled architecture. And we'll talk about later how that enables both scalability and resilience. Okay. Amdahl's law, you've probably heard of, but it really applies to event-driven programming as well, not just to parallel programming, embarrassingly parallel and stuff like that. Amdahl's law is one of the classic sort of computer science laws. I mean, you have Moore's law, you have Amdahl's law. Amdahl's law is really the one that is going to hit us in the future if we don't get this right, I think. So you have on the vertical axis here, you have the speed up in times, up to 20 times. On the horizontal axis, we have the number of processors. And we can see even if our system is 95% parallel, you can say 95% fully event-driven, non-blocking, then we still just get 20% speed, or 20 times speed up. It doesn't matter if I add, 8,000 processors, 10,000, 100,000 processors, on multiple machines, of course. It really doesn't matter because you can't get any more than 20x speed up. If you only get to 90x or 90% parallel, then you hit the limit at 10x. So this like 10 or 5 last percentage really matters. It doesn't matter if your application is sort of reactive all the way down to the database, for example, and you do blocking calls on JDBC there. That might be your last 10%. That means that you have put a cap on how much you can scale. So it really needs to be reactive from top to bottom. Okay, and this is why we need to start lobbying for like all the people using Oracle here. I mean there are no non-blocking or fully reactive JDBC APIs. I don't know if it's even really planned. I mean, MySQL and Postgres have implemented proprietary APIs, sure, but the database, the SQL database world, really need to catch up here. The NoSQL database world is a little bit better off. So I think in general we need better tools. Some of the ones I'm going to talk about here quickly are Actors, Agents, Futures, and Reactive Extensions. So Actors are all about sharing nothing. You avoid this problem of locks and share mutable state by just saying we don't do it at all. Okay? Instead, your processes communicate through messages, so it's fully event-based. And each little actor has a mailbox, and you talk to it by sending it a message, by putting it on the mailbox. And the nice thing here is that since things are completely decoupled, as we will see later, this really proves a very good foundation for scaling out as well. You have what is called actor refs. You never communicate directly with actor instances. Instead, you talk to the actor ref. This means that the actor instance can actually reside anywhere, and it can even move around depending on how the application is being used. Okay, it provides what we call location transparency. I'll talk more about that later. Okay, so if we take a look at the little Akka actor here, when you create an actor, you first have to define the messages that it should be able to respond to. This is a little greeting actor in Java. So we create this greeting message. It basically just says string who, and then we create the greeting actor. And then we define the behavior. What should it do when it receives a message? When it pulls it out of the mailbox? In this case, just print out. And now, if this actor has state, it's fully sort of secure to modify that as much as you want, since no other actor can peek in and modify that state. They are completely isolated. In Erlang, they're actually isolated all the way down onto the actual JVM or VM, the Erlang virtual machine. Akka runs on Java, so we need to do it, I mean, as much as you can, but if you call through reflection, for example, you can violate that guarantee. But I think we can get pretty far on the JVM as well. Agents is a different thing. It's like reactive memory cells. Instead of as an actor, you have the behavior, and you send immutable state to the behavior and have it update itself. Agents does the inverse. You have immutable state in like a memory cell, reactive memory cell, and you send the behavior to have that atomically update the immutable state. Okay. Else is fairly similar. It's backed by queue. You send it events, but in this case behaviors, and they are then like eventually pulled off the queue and applied to the agent. Okay, we have agents in Akka as well. They look like this. You create an agent. Here's an example in Scala. Agent with a memory cell of just 5 as an int, and then you can send update functions. They are sent atomically, or they updated atomically when they are pulled from the queue. Ordering matters here as well, so it will be in the order that you actually apply these functions. Okay, futures is another thing that we actually get in Java 8 now. I mean, decent futures. Futures pre-Java 8, I think, was not even worth the name. So if you think when you hear future, you think Java concurrent future. In pre-Java 8, you should like scratch that from your head. It's really completely broken type of future, I'd say. Now we finally get real futures, and why I think they're broken is because the only way to get a value out of those is to block the thread and get the value out. The futures that we have in Scala and we also make available in Java through Akka are completely non-blocking and allows you to compose things in a non-blocking, fully event-driven fashion. Okay. One example here is that you can create 3 different futures here, and then you can use this Scala for expression, for comprehension, to get the result out of each of these futures and compose a new result. And the thing is that this will actually not perform the calculation. This will just set up basically a data flow graph, how it should be processed. So out here, the sum here is actually also a future. So it allows you to compose futures and get futures out, and then defer the execution for later in a completely non-blocking fashion. This is, for example, used a lot in Play to do like reactive composition, calling out to different web services, do the composition in a not fully non-blocking fashion, and then return the result to the browser. Reactive extensions is another thing. It's also pretty nice. It came out of Microsoft. It was popularized in the Java world through Ben Christensen's Netflix old project at Netflix. They created an RxJava extension. It's really nice because they sort of built on the concept of futures, but it's It's like extending it to work with streams. Futures are like one-off things, like syncs. Like you can set a future once and then game is over. Reactive extensions allow you to work with stream of events and do composition on those. Okay, you can say that it turns regular iterable into push instead of an iterator. I mean, an iterator you pull things right until you reach the end of it. But in reactive extensions, you register to be notified and you get pushed the things that come into the stream. And so it's very reactive in that sense, fully non-blocking. Nice. Here is an example from RxJava. You get an observable here. That's sort of the stream from the network. And then it allows you to use the combinators, like the functional term, but like map, flat map, and filter and these things. So here we can say we should skip the first 10. We should take the second, the 5 that comes right after. We should map them. That means that we should transform them. So here we should add the is transformed after, and then pass it on into the subscribe function where we can register a callback to say I want to be notified now whenever a new event comes in that have been transformed, and so on. You can do lots more here, and that's also a nice way of, a reactive way of dealing with like data streams. Okay, I think the essence throughout all of these examples is that you should work in layers of complexity. I think you should, instead of as we're almost used to now, right, run into the problem thinking threads, locks, yeah, we take that for granted, that's the way we should use it. We should take a step back and say, can we solve the problem with a pure deterministic, declarative, and immutable core? If that's true, I mean, then we should resort to logic and functional programming, like Futures, Dataflow, that is fully deterministic. If we need to add determinism, non-determinism, we should do it selectively. We shouldn't do it all over the place by adding threads, right? That means that our system will be completely incomprehensible like at once. Instead, we should add it selectively only where we need it, because it has a very high cost. There we can use actors, Rx, iterates, agent-based programming, and so on. And if we need shared mutable state, if we really need it, I think we should first consider using transactions. And as a final step, if we really need it, or for performance reasons perhaps, because each one of these layers, of course, add a little bit of overhead, we should resort to like threads, pure monitors, volatile variable, compare and swap, all these kind of really low-level hard stuff, right? But that I think are better solved higher up in the stack using frameworks. So that was event-driven. Scalable. Scalable is defined by Merriam-Webster as capable of being easily expanded and upgraded on demand. Okay? This sort of defines the essence. First, I just want to say that I think that there's a lot of confusion between performance and scalability. What is what? Some people say they have a performance problem when they really have a scalability problem, and vice versa. I see that a lot. And they are very different things. They are so different that they're actually a trade-off from each other. You can't get both. Okay? So how do I know if I have a performance problem? My system is slow for a single user. Okay? Then I have a performance problem, or 5 users, right? How do I know if I have a scalability problem? If it's fast for a single user, but really, really slow under heavy load. It's too highly contended. For example, I've grown out of running it on a single machine because I'm CPU bound or I'm IO bound. I need to add more machines, etc. These are fundamentally very different problems and need to be addressed differently. Not saying that they are either one of them are more important than the other. Both matters. So when it comes to scalability as well, if we now talk about mainly scaling out, scaling up is more or less solved by being event-driven. Okay, you're really using the cores on the machine well. If we talk about scaling out now, we're dealing with the network, and the network is inherently unreliable. I mean, you can pretend it's not, right? And hope for the best. Go to church and pay your taxes, but it really doesn't help much, right? Actually, I really encourage you to read this excellent post. It's terrifying. It's like worse than the worst Stephen King novel I've read. I mean, it really lists everything that can go wrong if you have a network as part of your application. So that's something that it fundamentally changes how you design software. Okay, so I would talk about a couple of rants here. I mean, fallacy number one is that it's transparent distributed computing. I don't believe in that. Distributed shared mutable state, I think, is evil to the power of n, and n is the number of nodes. Try to avoid it, right? There are places where you need consensus. I'm not saying that's only evil, but it's the wrong default. Eventually, consistency is usually the way better default. Then add the cost of full consistency where you really need it. Everything has a high price here. Same thing with distributed objects like DCOM, Corba, all these things. Like Martin Fowler said it really well when he said it sucks like an inverted hurricane. I mean, if you've experienced the pain going through that, you know what I'm talking about. Distributed transactions, XA transactions, and so I mean, luckily the world has moved away from that. It's too hard to get right, especially with good performance and scalability. That said, there's been a lot of interesting work being done now lately when it comes to distributed transactions, like Peter Bailey's, for example, the highly available transactions and so on, like trying to actually run transactional systems with less guarantees, but still very, very useful semantics in a fully highly available environment. Some good reading here. I mean, the classic seminal paper, Note on Distributed Computing, and this one by Vernon Vogels are good reference material. RPC is another thing, I think. I think it's just the whole idea of emulating synchronous method dispatch, like pretending that we're in the same process on the network is bad. RPC falls in this category. Unless RPC does like Finagle, for example, Twitter's Finagle, where actually exposes a fully asynchronous non-blocking API as part of RPC. But I'm talking about RPC in the classic sense here. Blocking RPC, like pretending, like lying, basically. Do some hand waving and hope for the best. The problem is that it ignores a lot of things like you have on the network, like latency, partial failures, etc. Good reading here, Stephen Oski's Convenience over Correctness really goes through all the problems you might see with RPC systems. Instead, I'd say embrace the network fully, make it explicit, use asynchronous message passing, and be done with it. So building on the event-driven core, if we have an event-driven core, we already have a system where we send messages, where everything is fully decoupled, where location doesn't matter. Okay? It can be anywhere. You're already set up your system to be fully scalable. Why introduce these programmer convenience things, right? It just makes things worse. I mean, it's nice in blue sky scenarios, right? Because it just feels like home, feels like we're running in a single process on a single core. But, I mean, as soon as things start falling down, you're screwed. You need to hack into the product, or you will go around like miles around to try to solve the problem. So what we need is location transparency. And that is, as I said, enabled through event-driven and the loosely coupled nature of event-driven programming. So what is location transparency? If we take a look at an Akka example here, this is how you create an actor in Akka. You have your actor system. You say actor of, and this is the configuration object. We call it props. You pass it in the class, and then the name of the actor. Here we create a local actor, okay, local greeter, and we talk to it like this. We tell it by sending a message. I'm sending Jonas here to greet myself. Okay. Now, this is a remote greeter. Okay. Do you see any difference? There is no difference. That is location transparency. Location doesn't matter. it's all driven either through configuration or driven through the runtime, how the runtime sort of thinks that the system is best optimized now. And that can change. You can move things around as you add new nodes, etc. It's the only way of truly scaling and keep your sanity, I think. Not having to worry about topologies. That's something you should not hard code into your application. That's something that you should either let your ops guys do, or even better, being let the runtime do, to learn how the application is being used. Then you can spin up new machines and take them down, and it really doesn't matter. Your code looks the same. Okay, so I was planning on running a little demo. Now we have this tool called Typesafe Activator. I don't know how many have heard about that. Oh, like 1/3. So it's a great getting started tool. It's a great tool for learning. It's basically an interactive tutorial that you can use as a starting point as an editing tool, but as soon as you're getting you want to do some really core stuff, then you open it up in Eclipse and so on. You download it here from typesafe.com platform, get started, and the good thing is that it's not just our templates, it's really starting to take off. So we have a full repository of templates for any kind of a reactive application you might want to build. If you have an Angular or Knockout or MongoDB or whatever, this is you can do it here. Okay, so oops. So I just downloaded the latest version, and I was just showing it to Matthias, and it failed. So it was the demo daemon. No, it was my installation, but I reinstalled it and it worked fine. So here I've already downloaded the Akka clustering sample. I'm just going to try to show you what full location transparency can look like. So we can open it up here, and so see here we have a tutorial that can sort of walk you through what's happening, and here you have the code browser. So now we can open up the main first. I don't know if you can see this all the way in the back. We can just minimize this. So here we start up a 3-node cluster in Akka. All in the main, which is pretty neat. First we create an actor system 1, then we create the system 2 and a system 3. Then we attach each system here to a cluster, meaning that we run it in the cluster node. And we also get the address of the first one. And what I'm doing first, in the first node, I'm joining myself, because I need to join nodes to form a cluster. I won't go into much detail here. It's like epidemic gossiping, very similar to React, Cassandra. That's the way it has. You can have seed nodes, or you can apply them, or you can add them manually, as I'm doing now. And here the second node joins the first one, and the third node joins the first one. Okay. Then what I can do here is that then I can, for example, register a member listener. I'm not going to use that here, but here you can subscribe to membership changes. But what I was going to get at here is that you can create this chat client here, and here we have wrapped up a sort of distributed pub sub implementation based on Akka that you can just use out of the box. So here I'm creating this distributed pub sub extensions. I'm defining 2 interesting messages. First, I want to publish messages, and I want to receive the message I was published. So what this, I should have said that what this implementation, the little app does is implementing a chat application, like the hello world of the distributed computing, you can say. So I'm having a topic, chat room, and I'm subscribing. I'm letting each chat client subscribe to that topic by registering itself as a listener, and the name of the topic. Then it sort of is ready to listen for two types of messages. First is where the user send publish this message, which is then passed to the mediator and then fanned out to all the subscribers. And then all the subscribers will then get this message and then print it out, basically. And you can see this random user here. What it does, it just has a lot of sort of funny quotes that it just sends out in a random fashion, basically, by sending it to the client, by publishing the message to the client. So what we can do here now is go to the Run tab. I'm restarting the app, And here you can see that first I'm starting up node 1. Kathy and Ben join. They reside on node 1. Then 5 seconds later, I'm starting up node 2. Sky is running there. And 10 seconds later, I'm starting up the third node. And Miguel and Tyler are joining. And then they start collaborating. And as you see, it's not much code, right? I mean, starting up the cluster is like 20 lines of code maximum. And then you just have the pub sub mediator. The reason why it's so simple is because we have location transparency. We have these actor refs that doesn't sort of reveal where their running instance currently is. I could actually add new nodes here, and they will subscribe, and they will get the same message, or I can take them down. So it's fully elastic in that sense. So I really believe that, I'm just going to shut this down. I really believe that location transparency matters, and it's enabled through the nature of a fully event-based system. With your logic reified as events, as workflow, and the loose coupling, meaning that the location where the guy you talk to does not matter. Okay? And this becomes even more important in the resilience part. I will show you later. So by the way, so this is a little editor I can do. It doesn't matter if it's Java or Scala, but so I can edit code here. But of course, if you want to do this freely, you can open it up in Eclipse or IntelliJ. This is just a way of getting started and to sort of get a feel for what reactive programming is all about and so on. And as I said, there's a whole ton of different templates. I think I have internet. I might be able to actually show. Now there's 39 different ones. You can filter by tags with like Spray, REST, Angular, JavaScript. You have it all, databases, all kinds of stuff there. So, oops. So that was scalability. Now let's talk about resilience. Resilience is defined as the ability of a substance or object to spring back into shape. Like something's gone wrong, and now it's back, okay? Or the capacity to recover quickly from difficulties. That's Merriam-Webster's definition. I think it really fits well with what we're trying to accomplish here. So if we first take a step back and look at how failure recovery is done historically in Java, C, C++, and so on, we unfortunately have taken too much for granted, being the only way, even though it's the only way to really get screwed. The problem, I'd say, is that you're giving a single thread of control. What I mean by that is that you run your business logic, and since you were called by someone through the call stack, right? Each stack frame. And since each method call are in the same sort of line of stack frames, meaning running on the same thread, that means that if something goes wrong there, what's going to happen? You're going to get an exception like popping the whole stack, and at best you get sort of a stack trace out in your console all the way up to your new thread allocation or your Java executor service, right? So since you only have this single thread of control, you need to make sure that all your error handling also happens there. It means that your error handling will be fully tangled with your business logic, right? Because there's really no way of finding out that that thread actually went down. There's no notification scheme. The thing is that exceptions you can't subscribe on exceptions. You can only catch them higher up. And this leads to very defensive programming. As I said, where the error handling is fully tangled with the business logic. That's why we see in most cases in Java apps, in good Java apps, that you have try-catches basically everywhere, because things can go wrong almost everywhere if you have shared mutable state. And it's hard to keep your sanity doing this. I think we can do a lot better. So I think we should go back and see how do other industries solve it. For example, ship construction. How do they solve these kind of problems? Okay, I think the right way is to do like them. Isolate the failure, into compartments, okay? Just as you do in ship construction at the image tried to illustrate here. This means that if one of these compartments gets ripped up, it gets filled up with water, it will not affect the rest of the system. The rest of when the full ship is fine, it can sail on. Right, unless, you rip up all of them, of course, which can happen. You can get an out-of-memory exception, for example, in Java. That's like ripping up all of them. It's nothing you can do, really, unless you have another ship, right? Then you can put your personnel off, or you can sail off and let one of them sink, right? And you get the analogy. You need to manage failure locally, and you need to have a way of notifying then other cells that this guy went down. And this scheme gives you a way of avoiding cascading failures, okay? So what we need is some sort of supervision. We need to make sure that these failures are reified and propagated to someone that is healthy, that can actually do something. Either restart the component or send an email to sysadmin or doing something, okay? So I really believe in the sort of the Erlang way. I think I owe them a lot, and my wife as well. All the long nights scratching my head and trying to fix these things. Now I can try to be a good husband instead. So I really believe that supervision is the way to go, and it was Erlang sort of that popularized this idea. It's an old proven technology or technique in the telecom industry. They've been using this for 20-25 years. It's just in Java we've been so stuck in exceptions, threads, try catch. Okay, so instead of having, as I said, a way of reifying error, send them async. If we have an event-driven core, this is fine. We can just, if something happens, we can catch it, exception, because we still have exceptions on the JVM, right? We can catch it, we can let the runtime catch it, and then send and notify someone that can deal with it, okay? We call that the supervisor. So the supervisor managing the failure can kill, restart, suspend, resume, notify, escalate, do something. And what we get here now is instead of getting a system where we code defensively, hope for the best, we get a system where we actually managing failure at its core. Failure is just an event. If we're in an event-driven system, events are semantics, right? This means that we actually embrace failure as something that's natural. And that's very important, I think. Because things will go wrong, regardless how much you're paying and how much taxes you pay, right? So we better have a good way of dealing with it. And one way of doing it is use the actor model. That's like my sort of silver bullet, in quotes, to fixing this problem. Okay? So supervision in Akka. Actually, if you don't define anything, there is a default supervisor strategy that escalates on certain exceptions, restarts on others, etc. So some sensible defaults. But that can be overridden, and I'm just going to show you how you override it here, just to show you how it can look. It looks a little bit slicker in Scala, I have to say, but that doesn't look that bad in Java, and it will look a lot better in Java 8. Since we don't have lambdas yet here. But what you basically do, you have an actor here, and you create a one-for-one strategy. That means that the actor, this guy, this is not the supervisor. So I'm defining how my children, the guys I create, okay, the other objects, other actors I create, will respond to failure. Okay, so I'm creating a directive here, and I'm saying, for example, here I'm getting my exception. If I have an arithmetic exception, I should resume the component. Then it was fine. Hopefully it won't happen again. Probably user input. Hopefully the user doesn't passing in 0 again, for example, if it's division by 0. If it's a null pointer, yeah, then probably something in the actor's state is wrong. Then we should wipe it and restart the computation from scratch. Might be a programmer error, hopefully not. Hopefully it's just something here as well, some bad user input, you got the invariance didn't hold or whatever. we restart. And if else, we should escalate, for example. So here you actually get this organizational way of looking at things, where the workers try to do their best. If things go wrong, their supervisors try to help them by coaching them or whatever. And if things really go terribly wrong, it gets escalated. Sometimes all the way up to the CEO, and the CEO say, okay, sorry guys, we're out of money, we're bankrupt, or something like that. Okay. So if we now have this directive, this means that when all actors that this guy creates will be managed. And the nice thing is now failure is fully, as I said, fully decoupled from the business logic, and secondly, is declarative, which is also nice. This is easy to reason about. It's all in one place. It's very clear what's happening. Okay. Responsive is the fourth key trait, and this is something that cuts across all of these other traits, I think. If your system is not responsive, then it doesn't matter how good it scales or how event-driven and nice it is and how upgradable or whatever. Users will not be happy anyway. Okay? So I think the key point is that you need to keep latency consistent under both traffic bursts, when there's spikes. Need to be a way of handling those spikes, okay? And failures. You need to be fully responsive under failure as well. So the system needs to be always responsive. And that's more easily said and done, but there are techniques. Using in the fully event-driven non-blocking core, I think was like the key to get this done as well. Some other techniques are to use back pressure, for example, and that's very easy in an event-driven system. Then you normally have queues, and you have actually a way of managing backoff strategies. Okay. One of the classic sort of laws, it's an extremely simple law, but it's very useful if you actually gather stats and plot it out. It's Little's law. Little's law says that the queue length is equal to the arrival rate times the response time. Okay. This is like very simple queuing theory. This means that the response time, simple math, right, is equal to the queue length divided by the arrival rate. Okay? So this means that we actually have a formula now for plotting out. We have the response time on the vertical axis and the number of messages in the queue on the horizontal axis. And if we plot this out now, we usually get something like this hockey stick kind of look. And the important thing is then to go in here and say, okay, this is the place where we should apply back pressure. It's very clear now that this is when things really starting to go bad. Response time goes straight off the roof. If we make sure that we apply back pressure, meaning that we limit the number of messages that's possible in the queue to here, then we actually keep the system responsive. Okay. And another thing that can help is batching. If we sort of outline the full stack of the application all the way down to the NIC, if you use some sort of distributed system, right? Then you have the application. You go down to the NIO layer, the JVM layer, the user kernel space, TCP/IP layer, Ethernet, and then down to the physical NIC. It's extremely costly to traverse this for every single message, right? Then batching can really help. To do batching in the application layer and to make one round trip sending the whole thing out. This is what's like very, very simple classic trick. And most good tools do this for you already, CRMQ, whatever you use. But it could be good to know, to think about it. And another great pattern is by Martin Thompson. The name is not ideal, I think, and I think Martin agrees with that, but it's a really nice sort of pattern to help with responsiveness. It's called smart batching. So this is from his blog as well, this image. I didn't want to redraw it. So let's say that we have a system here. We have a bunch of publishers, producers, and we have one highly contended resource. It can be an IO device, for example, or something else. It's always contention that comes back and bite you. That's where things starting to go wrong. Okay. So that's what we want to get rid of as much as possible. If we then instead add, in Martin's blog here, he talks about the disruptor So that's why you have a ring buffer here. But it really doesn't matter if it's a disruptor, or you can put an Akka actor there or something. The important thing is that you have this facade that basically just grabs as much as it can in a specific time interval, and then takes the whole batch and pushes it down into the I device, now fully uncontended. This can really help with both throughput and lower latency, even though I think in a lot of cases this is actually a trade-off. In lots of cases, this is actually both lower latency and increasing throughput. And it's all thanks to having an event-driven system and using something like actors that makes it easy to work with design patterns like this. Okay. Another thing is important when it comes to the responsive trait is to be responsive to users. I mean, not just any user. I mean, a user can be a service, a user can be a subsystem, but actual users. I mean, writing really reactive web and mobile apps. So one way of doing that, I mean, I'd say the keys or building blocks in doing that is to have a way of doing reactive requests. I mean, async and non-blocking request response. Actually being able to compose these reactive requests and still be non-blocking. Being able to do reactive push, streaming things out to in a push fashion, not polling. Polling costs resources, CPU resources and something like that, for really no good reason. And do it in a two-way way. Okay, so if we do this, we can really build systems or UIs, I'd say, that are fully interactive with good collaborative data synchronization, both with the client server as well as user, right? And you can get this real-time feel if you have a system that's responsive all the way down, of course. So if we look at how you can do reactive composition in play, first I just want to show you how to create a controller in play. This is a completely static controller, but you have an application, your extends controller, you create the method, and that method is what you use in your routes file then to redirect. So everything is just plain Java code all the way through. So now what we can do is add a method like this, and as you can see here, we say, oh, this is an action that is async, so it's a fully async action. And now we can actually do a full reactive composition here. We can do two different calls out. Get tweets here by symbol, for example. What we get back here is a regular Scala future, which allows us to do another call here and compose that. And the result, we can just turn to JSON and return to the user. This just does fully non-blocking function composition. It doesn't say do this first and do this now, blocking, waiting for the result to return. Okay, it's fully reactive, which is very neat. This is very similar to the futures example as I showed you. Okay, using the Scala 4 comprehensions. You don't have to do that. You can use map, for example, as well to compose things, map, flat map, and so on. Okay. So now I have 7 minutes. I was just thinking going through a quick demo here as well, a more rich application that shows you both Akka in play and some knockout, I think it is, if I remember correctly. So let's see here. Oh, I can't see everything. So go back here. So this is the reactive stocks applications. I'm opening that up now, and the nice thing here is that it has a fully interactive tutorial, as I say, so you can explore this by yourself. So if we take it through the tutorial here, you can say we first have a routes file here. If we hit the WS URL here, what we see, then we redirect here to the application.ws method, because I mean routes are just methods, right? So if we then go down to see the app, and we go down to the controller and now the application, we can see here that here is our method. Okay, and this is where the WebSocket action happens. The first thing we do here is that we create a user actor. By the way, this is an application that sort of shows you. It does. it's sort of a toy application that goes out on Twitter, that does some query, and then comes back and gives you a proposal if you should buy or sell a certain stock, right? So you should not use that as advice if you should really go buy. And so don't come to me and complain if you did that. But it's a sort of toy application that really shows your reactive composition all the way down. So here we create a user actor. And in the WebSocket, if we get a WebSocket invocation here, then we create a watch stock message, and we send that to the stocks actor. The stocks actor is the actor that manages the stock actors. So you have a stocks actor holds many stock actors. Okay, each one for each stock that we want to monitor. Okay, so now if we go down to the stock actor. You can see this is a joint like Scala Java example to show you how. I mean, you can pick whatever you want in our. You can write your system fully in Java or Scala or both. It really doesn't matter. So here we have our stocks actor. When we get this watch stock, what we do then is that we look for our user actor by symbol, and if we don't have it, get or else. I mean, if it returns empty, then we create a stock actor, and then we forward the stock sort of message to our stock actor, and the stock actor is here. So we have one stock actor per symbol, and we get this watch stock message, and we send it off to the user. Okay, and the user now gets the stock history to be able to be displayed up in the browser. So you can see here the user actor. I don't know if you saw that, but it is created by getting a reference to the WebSocket. So whatever it can do, it can utilize the WebSocket and push things out. So now if it receives, for example, in this case now the stock history, you can just create a JSON object and just write it out straight out to the WebSocket up. In a fully non-blocking reactive fashion. So now we're able to receive things from the WebSocket. We go to the stocks actor, to the stock actor, that forwards it to the user that pushes it straight up. Okay. So now we covered reactive push. If we now go to the reactive UI here, so let's see how this all ties together. We can see here this is the simple like play template. Here we create, we set up the WebSocket, and then we have some simple coffee script here to just make it all work in the browser. So here we instantiate the WebSocket. If we get the stock history that, if you remember, the user created and like pushed out through the WebSocket, we call populate stock history, and it's fully reactively displayed. Or if we get a stock update, we push that out. There's more to it than this, but this sort of ties together a full reactive application. And it really highlights that it needs to be reactive all the way down. It needs to be fully reactive from the user UI through reactive call, doing reactive composition at the end, going down to the Akka backend. The Akka backend could use the distributed sort of pub sub, or it can go down to push it down through, for example, reactive Mongo, which is a very nice Mongo driver that is also fully reactive. And if you do that, then you get a system that's really extremely responsive, that can be fully resilient, and also scale as much as you want, because there's really no bottleneck here. So going back to the slides. So the essence, what I try to walk you through here, is that if we built our application on an event-driven foundation and are fully non-blocking and asynchronous, then we also get the loose coupling, which enables us to scale. We get location transparency that allows us to scale, horizontally to as many nodes as you want. If you have a share nothing architecture, there's really nothing that limits us for how much we can scale. And this loose coupling and the event driven also allows us to reify the events and send them as regular events, meaning being fully part of our workflow, meaning embracing failure as something that's not really exceptional, and have a good way of managing it. And the nice thing that I haven't said, but that is key as well, is if you have location transparency and a model for managing failure based on events, this means that the same semantic holds on the cluster. It means this supervision that I just talked about is just events talking to a supervisor. It doesn't matter where that supervisor is. That means that your model scales both through your workflow as well as the way you're managing failure fully on the cloud without any changes. It's all driven through configuration. The code is the same. I think that's really, really nice. So one thing that one document that I've been part of writing, along with a whole bunch of other experts way smarter than me, is the Reactive Manifesto. And this Reactive Manifesto is available at reactivemanifesto.org. I encourage you to go there, read it through. It goes into even more detail than my talk here about each one of these traits, how they're all connected. And if you agree with it, you can sign it. There's already 2,500 people that signed it. And the reason for this, for creating this, is to build a common vocabulary that can bridge communities, because a lot of different communities do this. The JavaScript community, I mean, they have great stuff for this, Knockout, Angular, and you name it. The .NET community, I mean, they have the Async library, if you know that. I mean, they have Rx, Reactive Extensions. There's happening lots of stuff in Java. And reactive programming is truly polyglot. You can't do it all in Java. I mean, the systems are way too complicated for that. So this is why we need one way of talking about things, one way of sort of bridging things. And I think the Reactive Manifesto really helps with that, because it brings the discussion back to principles, concepts, rather than APIs and the nitty-gritty details. And it tries to establish a common vocabulary so we have the same way of talking about things. Okay? So that was everything. I'm 1 minute over time. That's everything I had to say. Please feel free to email me or go to typesafe.com if you want to find out more. I'm happy to take questions afterwards. I'll be here the rest of the evening. So thank you.